It's great to have technically savvy folks here. Thank you for having me. This is the first time I've ever been to Salt Lake Community College, and I know it's really nice outside, and I wish we could all be outside, but I'll get to show some pictures of the great outdoors. So today I want to talk about different frontiers that are happening in both Earth and planetary science, and in particular talk about examples of an area that's very close to us, our state of Utah, and how we might extend some of those ideas to Mars. And this might seem a little bit out there, but to first kind of back up a little bit, I wanted to talk about some of the perceptions that we have. And so typically, a lot of our perceptions are shaped by what data are available to us. So first of all, when we're young, we might have a perception of Mars that looks something like this. And this is not a stage where we can take in a lot of data. But as we get older, maybe our perception of Mars changes to something like this. I think many of you know of Marvin the Martian. And then as we get maybe a little bit older, maybe our perceptions of Martians might have been like this. Probably most of you have never heard of this. It might have been a show that was on TV in the age of your parents, or maybe even your grandparents, I'm not sure. But this was an image of Mars. And then as you get older, perhaps you dig in even deeper to more sophisticated ideas of Mars, like some of the science fiction. And one of the reasons why the science fiction seems so fun is that there are pieces of data in there that are incorporated into the story, and it makes it seem like it could be more realistic or more plausible. So one thing I want to emphasize is how data is changing in our perception of Mars from some of the science perspective. So here you have an image in 1976. I think that is before most of you were born. And there was a very popular idea that there was this face on Mars, and that face was looking back at the rest of the universe. And so here's a picture of this face. But during the 1970s, the resolution of data was very coarse. And so in the 60s, 70s, maybe we could distinguish something that was about the size of a house. So that's pretty poor resolution. And what you can see is that over time, here are some other images from 1976, 1998. By 2001, it was very clear that this particular feature is just a landform, just a natural landform. But with the low resolution, it sort of did look like a face. But when you have higher resolution, you can see very much the details that say this is just a landform. So by 2010, what's happened is that some of the orbital imagery is able to get resolution down to the size of a piece of paper, about 30 centimeters per pixel. And so this is the tremendous difference in why our perceptions of Mars are changing, because the data is much better and the resolution is much higher. So as we're talking about frontiers, frontiers in my mind are areas that are new or uncharted territories that we want to explore. And a lot of the explorations has happened with some of these rovers. This was the first generation rover, which was called Sojourner, that went to Mars. And this was kind of the McDonald's of rovers. It was faster and cheaper. But what we found is that we wanted to do more things than just kind of scoot around. We wanted to be able to do more analyses. So the rovers got bigger and they got heavier payloads. So this was the Mars Exploration Rover Opportunity, and then the one Mars Science Laboratory Curiosity that is now about the size of a Mini Cooper and is the rover that's currently exploring Mars. So what I want to do is share just 3 short stories with you. And these stories are, number 1, talking about examples from Earth and how we use those to interpret Mars. Number 2, I want to talk about the combination of understanding life, the idea of astrobiology. And number 3, I want to talk about where are some of the new directions that science is going and how we're using technology for new developments in science. So we'll start first with Earth analogs. I'm not sure how many people have had geology in your maybe junior high curriculum, but maybe you've heard about the rock cycle, and there's 3 different types of rocks. Igneous rocks, as shown here, that are from hot magmas, metamorphic rocks that are subject to change, and sedimentary rocks that occur at the Earth's surface temperatures and pressures. So this might not be the kind of diagram that you're used to seeing, so I thought I'd introduce something that you maybe are more used to, and that is cars. So we can all relate to cars, and this is what igneous grains look like. They're fresh and pristine. They just came off of the press, and it's very clear what their origins were. If we look at metamorphic grains, they look something like this. These are ones that have been subjected to high pressure. So you had something that was pre-existing, but the shape of it has been changed due to pressure. And if we look at sedimentary grains, they would look something like this. I think you recognize that these are old VW bugs, which was a popular car. And VWs were very popular because they lasted a long time and they got beat up. And here are some of these at low temperatures and pressures. Sedimentary grains are the ones that are well traveled. They've been over the world maybe the equivalent of 2 to 3 times around the world. And part of the challenge is figuring out their history and where they've been. And in particular, one of the features that I'm interested in is called diagenesis. So you see this moss that's growing on the car. This is diagenesis. Dia meaning secondary and genesis mean origin. So after grains come to rest, there's often other things that happen to them, and that's part of the story that I'm interested in, diagenesis. Okay, so we're going to talk a little bit about these stories from Earth to Mars, and my interest actually started with a lot of the landscape in southern Utah. And I think most of you know it's just beautiful country down there, lots of different colors. And so I started looking at why sandstones were different colors, and I started noticing that places where some of the sandstone was multicolored, there were often some of these round marble type of things that we call Moki marbles, and maybe some of you have heard about them or seen them in a rock shop. And these are made also of the cement iron. And so these two features actually seem to be related to each other and seem to be part of a story that went together. So what we're seeing is that through these many studies of southern Utah, the rocks are color-coded. And color coding is good because that allows us to see things more easily. So a lot of this coloration means that the element iron has cycled through the rocks. And Mother Nature's artistic palette uses iron. Like that is the color that's really making a lot of the artistry. Along with these colors in the sandstone, we have these cemented mineral masses, which we call concretions. And these are just balls of better cemented sandstone, and these are also different colors. So these are some of the ones that are iron oxides that are brown. These are malachite that are green, and azurite that are blue. And even these colors are reflecting different mineral compositions and different waters. But both of these things together are telling us that waters were there, waters underground were moving and are responsible for some of these features that we see. Now, when you go down to many of the parks in southern Utah, we have these different layers, and we call this stratigraphy. And the layers here are just like a layered cake, and they're very nice and even and well exposed. And the rivers are like the knife that cuts through the cake and actually exposes the layers. So of all the layers on the Colorado Plateau, the one that I've been the most interested in and the one that is the most porous and has the greatest ability to transmit fluids is the Navajo sandstone. And so this is the one that's most like a porous sponge that could soak up waters and allow fluids to move through. And so this is one that often shows some of the greatest coloration and some of the greatest variety of these concretions. So the model that we've developed for these concretions is that probably early on you start off with red sands, fairly early in the history. And if you could look at the grain scale, these are grains that have just a very thin film of iron oxide coatings around them. But when these sediments get buried, waters migrate through and they can actually bleach the sandstone white and remove the iron and put it into solution. And then those solutions later meet with oxidizing conditions and reprecipitate the iron into these compact balls. So you can see that the distribution of iron goes from the feature on the left to these compact concentrated features that are on the right. And some of the fluids that might be responsible for this bleaching would be things like petroleum, methane, maybe even organic acids. Those are the ones that can chemically actually put some of the iron into solution. And so here you can see the white rim sandstone down in Canyonlands. It's white because of hydrocarbons that have migrated through. And if you can actually see some of the outcrops there in a remote area of the Laterite Basin, sometimes you can actually see the oil dripping out of the outcrop. And that's probably the closest that I've ever been to a Beverly Hillbillies experience where I could actually see the oil oozing out. So here is the model of what we think is happening. You have red sandstones, and you introduce certain types of fluids, reducing groundwaters, if I can get this to work. And then those reducing waters actually kind of bleach the sandstone, put the iron into solution, and dissolve the iron, so it's actually in the stage of what we call Fe2+. And then you introduce oxygenated groundwater conditions, and that change in the chemistry actually helps the iron reprecipitate, but now into these organized balls that we call concretions. So this is a story about how we get different colors of sandstone and how we get these different concretions. So I was one of the few people that was looking at some of these concretions here on Earth. And back in 2004, the rover Opportunity was sent to one of the equatorial regions of Mars because they knew that there was crystalline hematite there. And hematite typically forms in the presence of water. So the idea was, if we send a rover to this place where there's hematite, we'll follow the water. Maybe we'll be able to see signs of extraterrestrial life. What they were expecting is that the iron might be in these banded formations, and it was really much to their surprise that when the rover landed in this kind of ellipse area here of Meridiana Planum, this dot shows you where the rover landed. And this was one of the early images that the rover took. And you can see that this has thermal emission spectroscopy superimposed on it. So the different colors are representing different amounts of iron. There's high amounts of iron where it's red, there's low amounts of iron where it's white or colorless, and then there's intermediate amounts of iron in these kind of greenish and bluish colors. And these areas that are circular are actually where the rover balloon bounced and pushed some of the hematite spherules into the Martian soil. So this particular crater where the balloon bounced was called Eagle Crater, because if you play golf, it's like getting a good shot. So I think an eagle's a pretty good shot in golf. So they called it Eagle Crater. And you can see that the distribution of the iron is very similar to what we have in southern Utah. And this was down by St. George. So these would be high amounts of iron here where it's kind of red and you've got these accumulation of the concretions. The white would be where it's low amounts of iron, and then there are places where you would obviously have intermediate amounts of iron. So in comparing some of the pictures from Mars and those compared to Utah, what they found is that the iron seemed to be in these small little balls. And these are fairly small, only about 4 millimeters in diameter. So maybe about the size of a small blueberry. And they called them blueberries because if you could see it with your naked eye, it would kind of look like this blue color. And they also noticed that this has the false color superimposed on the iron. So wherever the iron is yellow, and you can see that the iron is in these blueberries, but the blueberries aren't touching each other in the rock. They're actually physically dispersed, and that is actually like blueberries in a muffin, you know. So they called those blueberries, and if we look on Earth, we see similar forms where we have iron-rich balls that are better cemented, and when you see these in the outcrop, they're often physically dispersed where they actually aren't even touching each other. And that's a product of how fluids actually move through saturated groundwater conditions, where all the pores are filled with water. So here's some examples of Mars shown on the left. You can see that in this strata, there's one blueberry that's poking out right here, and this one has a ridge on it. And there's just slight differences in the texture of the rock that cause the fluids to move a little bit differently. And you can see the same type of thing in rocks in Utah. Some of these concretions have ridges on them. Some of them even look like flying saucers. And it's because the porosity or the permeability, the pore space along this lamina are just slightly different. Some other things that were interesting were these conjoined forms, and there were both doublets and triplets found on Mars, and we find that the same kinds of features occur on Earth. And in fact, we have doublets such as the ones shown here, and we have triplets where there's 3 of these balls that look like they're stuck together. And some people ask me, why do the triplets on Mars look like snowmen and the triplets on Earth look like Mickey Mouse ears? Well, actually, we can get all kinds on Earth, and we can get the kinds that even look like snowmen. And you can see that some of them can even look like these spiky balls or a cluster of grapes. And these are some different sizes that we have on Earth, from things that look like a golf ball size all the way down to these very small sizes that are about the size of a sand grain. And the blueberries on Mars are about this size right in here. And it turns out on Earth, the more common sizes are the small ones. It's more rare to find some of these big sizes. But there are a lot of similarities, and yet there's still a lot of differences on Earth. And so one of the questions is, why are the concretions on Earth different? Why do we get bigger sizes on Earth? Why do we get more of these forms that look these funny shapes that we haven't seen on Mars? And I'll show you some of my favorite pictures. This is from southern Utah, where these are very large concretions that are about the size of a grapefruit. Very unique locality. And then here's an area in southern Utah that one of my PhD students is studying. These are about the size of golf balls, beach balls. These are giant ones, you know, about 82 centimeters in diameter. And I asked my son to stand on one so you could actually get an idea of what the size of that is. And in southern Nevada, there's actually about a dozen of these kind of beach ball sized concretions. So why are we getting these different forms on Earth? It's taken me a while to think about this, and I finally have come to the conclusion that one of the reasons why things are different on Earth is because Earth is so permeated and saturated with life. And almost all waters probably near the surface or on the surface for the last 3.5 billion years have had microbial life in it. So literally, Earth is contaminated with life, and probably when we look at the Earth's surface, it's very difficult to even know what abiotic things look like. Even though you don't see life in some of these things, that doesn't mean that it isn't there or wasn't there, or maybe it has left some trace there. So one of the things that we find about concretions is that some of the remarkable concretions actually have fossils inside. And it's the fossils that are kind of like the flypaper that acts as the nucleus to gather up certain kind of chemical ions to preserve and better cement some of those areas. So here you can see a young person looking at a concretion here, and this has a big ammonite inside. Sometimes ammonites can make concretions that are as big as wagon wheels, just enormous types of things. Here are some remarkable examples where there's a crab that was preserved because of the cement that was preferentially gathered there right around that particular feature. So all kinds of concretions have fossils, but what if you don't have any fossils? What does that mean? So another mineral that's often involved in mineralization is pyrite and some other iron oxides. And what happened is what one of my colleagues, paleontologist Randy Ermis up at the U, wanted to look at dinosaurs. And he was finding dinosaur bones in a quarry in New Mexico. And these are some of the Triassic deposits. And what he noticed is that when he was looking for dinosaur bones in this quarry, wherever he found dinosaur bones, he often found concretions. And those concretions are a little different than the ones I showed you, but this is a cross-section of one of them. And they look like they have pyrite, goethite, and gypsum, which is the light color. And they're all associated with these bone beds. And in fact, the relationship was so good that they could use the concretions as an exploration tool. If they found concretions, they were pretty sure that they were going to find dinosaur bones if they just kept looking. But what was interesting is that the concretions are on the ends of the bones, like right here, and sometimes the concretions are even on the sides of the bones. So why would that be? Well, maybe at the ends of the bones, what do we typically have at the ends of the bones? We have cartilage, we have maybe some tissue, and maybe there's just enough of it there that it was acting as the nucleus to gather some of the mineralizing ions to that particular spot, and so that's where the concretions preferentially actually nucleate along some of those particular areas of the bones. So there's a very clear relationship often between concretions and organics or organic material. Now I just want to briefly mention that there's lots of examples of soft sediment deformation, and this is an area that is by the wave in in northern Arizona. And if you can't get to the wave, another really spectacular place is called White Pocket. And here we've taken a drone type of image, and you can see all these swirly types of patterns. And these types of swirly patterns also indicate water. Probably very high water table conditions in an ancient desert system. And just to kind of show you how we use these comparisons, I'm going to fade away to a picture of Mars, and you can see the similarities of those sinuous types of forms. We can only generate those with water, and so seeing these kinds of things on Mars and using the Earth analogs helps us interpret that there has been high groundwater table conditions on Mars. Okay, so I'm going to come back now to a second story, and that is about biology and how we use biology in some of our geology studies. So you've probably heard of astrobiology, which is the study of the universe, and this living universe contains things that we call extremophiles, organisms that can live in extreme conditions. We think about the origin of life. We think about what we call biosignatures, like is there just any little remnant or any little signature of life that we can detect that tells us that life was there? And are there certain kinds of environments where life is more likely to occur? And we call those habitable environments. So astrobiology includes all of these different things. And what we're seeing, that Earth is full of life. So when we're actually going out and exploring other planets, and we often use Earth as a comparison, it's really hard to know what an abiotic habitable planet looks like. Certainly Earth is habitable. We know that because there's life all over the place. But what would the planet look like if there wasn't life, but it still had all the right kinds of conditions? These are some of the things that the community is thinking about. And so we see that life has many expressions. And if we look at these blue arrows, these are all the things that can go into making different types of life forms. Different elements, water, energy, climate, tectonics, lots of different things. The environment, that all affects life. And then life has different expressions. And we can break up these expressions of life into these three branches here. We can have things where life is expressed in different substances, like maybe the organization of certain molecules or elements. We can have direct evidence like fossils, or we can have maybe concretions or stromatolites or different kinds of features that indicate that life is still there and has that trace. Or what if we just have certain kind of patterns? What if minerals are just organized a certain way and that's telling us that life was there? Because life is very good at adapting to things and taking what it wants. So here you see a concretion, and I used to think concretions might take a long time to form, but here we have a watch band. And you can see that this concretion just latched right onto that watch band, and so this had to maybe form in a matter of years, maybe 30 years or less. And that is probably because the waters that were involved had life in it, and so things could happen very quickly. So as we're thinking about different biosignatures, some things might be visible, but some might be invisible. And so if we look at this mineral pyrite, do you think that has life in it? We don't see any fossils in there. It's just it looks like an abiotic structure. Here's another example of pyrite, but now pyrite's in a different form. It's in this kind of round form, and it has these little, we might call these framboids, these little kind of knobs or little nibs there. So that's another form of pyrite. And then here's one that looks more massive that I'm sitting on. This was an example in China, and I thought this was a remarkable pyrite concretion. It's mostly the same mineral, although it does have some sand grains in it. And then here's another example of pyrite that this kind of knocked my socks off. Wow. This is where the pyrite has gone in and replaced a fossil, which was a sea lily, or what we call a crinoid. And there's just been this remarkable replacement, almost the way petrified wood forms. Just this replacement of one mineral for another mineral, and now you get this preservation in this really incredible fossil. So what is this? Is this non-life on the left and life on the right? Maybe that's what we would think. Initially, hey, stuff that looks like these cubes, that's got to be no life. Stuff that looks like this on the right, that's got to be life. But what about the stuff in between? There's probably a continuum, and maybe even though we can't see life on that, maybe this could be low life. So these are things that we're really trying to understand, and we have to figure out better ways to look at biosignatures maybe in some of these intermediate areas, because it's not going to have the same expression as we see over here on the right. So life is everywhere. It's hard to separate from geology. Geology often used to have these three corners saying there's physical processes, there's chemical processes, there's biological processes. But when we look at Earth, it's a combination of things. And when we even look in the cosmos, in the universe, it's probably going to be a combination of things. And at least on Earth, we have to recognize that probably the biological is much more important than we thought. Because it's probably affecting all these other things of physical and chemical processes. And so what I would encourage you to think about is that when we think about using Earth as an example, we have a bias. And that bias is because we are the water planet. We've got lots of water, and that means that we have lots of life, and that means that our sample is only n equals 1. And so we have to keep that in mind as we're actually trying to do comparisons and take examples from Earth to interpret other planets. So the future for astrobiology, this is something where I'm presenting different ideas that we have to think about. And as you look at this droplet of beautiful water, this has got the mineral copper in it, so that gives it this blue color. Even a little droplet like this has got microbes in it. And this is in a cave in Hawaii. And so we have to think about how would life get preserved if this precipitates out as a stalactite or a stalagmite? You know, would we be able to recognize that life was involved? Because we know that there's microbes in this. We can analyze it and actually see. So what we're saying here is that the future of studies of astrobiology really needs the appropriate instrumentation. And oftentimes we might have to look at a really small microscopic scale. It might not be something you can see with your naked eye. We also find that we need to have different kinds of standards. We don't really have standards for a division line where everything on this side is biotic and everything on the other side is abiotic. We don't have any sharp standards. We don't have any sharp boundaries or division lines. So we do need to have more standards, and maybe we can develop these in the laboratory. Another thing that's challenging is that life occurs across multiple scales, so we got to keep that in mind. And then an aspect that I want to talk about is how things are going to change in the future with different kinds of technology and data sharing. So the third story I wanted to tell you about is new directions of where Earth and planetary science is going. There are definitely changes in the wind, and what we see is that when we do geology, this is how we used to do it, 20 years ago. And we used to take notes in our Write in the Rain notebook, and that notebook would just go back on the shelf when we got back to the office, and then when we retire, it usually goes in the dumpster, and that's the end of that. And all that data that we collected is lost. But some of those areas aren't available to access anymore. Maybe it's private land, or maybe it's been covered up, or other types of things have happened. And so people are recognizing that we shouldn't just throw away all that data. And just because it's in a field notebook doesn't mean that it's irretrievable. And probably we shouldn't just be throwing those things out. Now, if you look at the way science is done now, this is doing field work the same way that we used to do it, but what's the difference here? This guy's more comfortable, and he's doing it on a laptop. But actually, in geology, more of our population is women. We're about half women. And I would have taken a picture with a woman on the computer, but all the women were on the outcrop, and the only one sitting down with the computer was the man. But this is a picture I got from someone else. And so this is actually the way we're doing science now. And about half of our population in geoscience is women. And so we are diversifying our science, and we're finding that we need different kinds of tools to use. So the National Science Foundation has recognized this, and what they have proposed is a project or a program that's called EarthCube. And they said we actually have to change the way we do science, the way we collect data, and the way we store data. And we need to be able to archive it and access it later. And so we can advance the science by actually leveraging the power of cyber infrastructure, using computerized technology. and even things like artificial intelligence or machine learning that I'm sure you've talked about, programming things so that something else, a computer, can do all the visual recognition and identification for us and do a job that's about 90% correct with maybe only 10% error. And so if we can leverage all of this type of available technology, we can actually better meet the grand challenges of our science. We can actually make new kinds of discoveries that we haven't been able to do before, or we can actually compare data sets that we haven't been able to do before. Your generation is very used to open data sharing. You're used to being able to go to Google and get whatever information you want. And it's because people are sharing data on the internet. And open data sharing has to happen more in our science. We can't just put our field notebook, on the shelf and just have it isolated there where nobody knows what it is. So we have to collect data digitally, or we have to transpose the analog data to a digital format so that we can share data. And I think the Google Earth platform is one that geologists love because we can actually visually see some of the relationships. And if you can imagine, what would it be like to have more of these computer programs that actually have the science information? So one of the projects that came out of EarthCube is called RockD. And RockD is something that you can do on your handheld device, and you can be anywhere that you want to be in the world, particularly in the US is where we have the most data. But using the GPS locality on your phone, it will tell you, give you a map, and the maps can be relief maps, topo maps, and geologic maps, and it can actually tell you what is the stratigraphy or what is the geology right underneath your feet, and it'll tell you what the units are underneath you. And so this is a really great thing for geologists because we used to have to carry around all these maps and think about where we were, but now you can have all that information at your fingertips. Another thing that we're doing that I'm a part of a project of is this program to actually do a better job of collecting field data. So now our field assistant is our handheld device, and we can actually collect data and actually make measurements and then actually upload the data to some database system later. And here you can see students are making measurements in the field with their tablets. And so this is actually now an effective way to collect our data. Some of the challenges that you can imagine are like what you see here. A lot of times we're outside, and it's not the same as being in an office where the light is really good, but outside in the bright sunlight, it's very hard to see the screens. And so here we are using umbrellas to try to get the right light so that we can see the screen. But the technology will surely change so that we'll be able to better see the screens even out in bright sunlight. So what if we could have Google type of information, Google Earth type of platform, and superimpose all of our science data onto that kind of visualization platform? Wow, that would be really great. And unfortunately, Google Earth, Google is not interested in partnering and doing that because they don't see that they're going to really benefit from it. But that's the type of thing that the direction that the science has to go in the future. You want to be able to go to a map, just click on it and say, show me all the fossils that have been collected at this point. Show me every place where the Navajo sandstone outcrops in southern Utah. Show me any study that's ever been done at this particular point. It would be amazing to have that kind of data and information at our fingertips. And recognizing that, NASA said we're going to try building our own platform and have a visualization map type of format, a platform, but we're going to be able to superimpose some of the data on that. And they've now done this for several planetary bodies. They've done it for the moon, where there was only 50 years worth of data, so it's pretty easy to put 50 years worth of data onto the platform. And now they're currently doing it for Mars, and they have plans for other ones. So I want to show you a little bit about how some of these visualization platforms can work with the combination of science. So this particular one is called Mars Treks. It's already available for free online, and I've just got a little video here with I hope a little music. So here you see the planet Mars. You can actually pan in and zoom at different types of scales that you want and look at different physical projections of the planet. You can look at data that are collected from any of these different missions. So you can say, what data was collected from this mission? Let me compare it to another one. So you can compare between data sets and actually be able to analyze and see different types of relationships. I mentioned that we have this high resolution data, and you can browse the planet for all the places that have that high resolution data and zoom in. You can actually perform calculations. You could just draw a line and say, give me the instantaneous elevation profile of that line. And maybe we could even do that with the geology layers underneath in the future. You could find out where the current orbiters are and what they're actually looking at any particular time with their localities. You could actually print out any kind of terrain. Just select an area and say, I want a 3D model of that. And you could print it out on your 3D printer. You could use different types of bookmarks, just like we would do on Google or Google Earth, Google Maps. You could actually have the data that's related to each of those spots, and you could actually mark different types of pathways. And this particular one is taking the example of the popular movie, The Martian, and actually using these pins or these bookmarks to show where Mark Watney would have gone to get to his traverse to get picked up and rescued by the mission. So this allows us to see a lot of the science that's related to individual places. It allows us to explore areas that you couldn't really do in the same kind of way because you have this access to information through these digital platforms. So this is kind of a preview of what we see as the wave of the future for much of the science. Not just earth science, biology, all the science really combined could be integrated together through the power of cyber technology. So the message that I want to leave with you is that cyber technology and science combined together is really a hot topic. And in fact, many of the computer scientists are looking and excited for the ways that they can take their knowledge and actually apply it to a real problem. They are eager to help the scientists. And I used to think, oh, they're just not going to be able to, program all these subtleties that I see in describing these rocks. And we were actually out on the field, outcrops, and I said, I want to be able to describe what the shape of this is. And they said, oh, yeah, we can do that. And I said, I want to be able to describe the depth of this particular texture. And they said, yeah, we can do that. So they, amazingly, they have ways to do that. And they're excited about finding ways to help us make new science discoveries. So the bottom line here is your generation is going to be able to make new discoveries. You're going to integrate new types of data that we haven't been able to do. You're going to be able to visualize it and see it in a way that makes it easier to take in and comprehend. And all of this cyber technology aids in networking. A lot of times you're just used to communicating regularly with people without really talking to them in person. And the same kind of thing can happen in science. We can actually share information and communicate and network because of this cyber technology. So to summarize what I've shared with you today, number one is that we have some fantastic examples of Earth analogs, and a lot of our Utah landscape is what we can use to help interpret what's going on Mars. And some of these early interpretations actually showed us that there was, in fact, water on Mars. But we do have to understand that we have a bias. When we look at Earth analogs, don't forget that everything on Earth is just kind of permeated with life. And so when we take that information, we have to really try to understand that so we can determine whether or not there is extraterrestrial life elsewhere in our universe. Number two, astrobiology and the integration of geology, biology. These fields, to really understand life, require the right kind of instrumentation. And we have to have the right kinds of standards. And I think your generation is going to be able to help do that. You're going to be able to do more high-powered microscopic work, more high resolution, and you're going to be able to compare multiple data sets, and you might be able to say, this is what abiotic really looks like. This is the division line for biotic. And that's really going to help move the science forward. The third thing is that artificial intelligence, cyber infrastructure, data management, all of these things, including big data, having multiple data sets, is going to allow you to make new discoveries. And I think one of the examples that I've been excited about is many of you maybe have used iNaturalist. And you just take your camera, your iPhone out, you take a picture of some critter that you see or some plant that you see or some bird, and then you upload that picture to iNaturalist and it tells you what it is and it identifies it with 90% accuracy. And the same kind of thing can happen where we might have visual things where we take a picture of something in a microscope and it says, yes, this is a biosignature and this is what it means. It's made by this particular cyanobacteria or whatever. So these are some of the things that are in the future. What I want to say to you is that there's lots of exciting frontiers that are on your horizons. And Earth and planetary science have been merged together in ways that were never possible in the past, and a lot of it's because of data, technology that's giving us resolution that we never had before. And I want to leave you with this one view that you are the next generation, and that you are the ones that are getting to see things that our generation never thought was possible. It's really exciting. Thank you. Yeah, that's a challenge. Some of the instrumentation that we're using here on Earth is Raman Spectroscopy. And so some of the talk has been how do we get some of the Raman instruments on some of the rovers, and maybe that will allow us to be able to detect things, but it's only right where the rover is. But when I talked about some of these other things like different kinds of patterns, if we see that a planetary body has a certain type of atmosphere and it has a certain kind of composition, does that composition in itself tell us that maybe life was there, because the only way you could get that composition is if you had life. So those are the kinds of things that I think are still out there that we don't know. Maybe there are some of those kinds of patterns that could be detected from afar, even physically not being there, but as of yet, they're patterns that we still don't really understand. Oh, what bleaches the rocks on the different planets and such? So on Earth, we do have hydrocarbons that can do bleaching, but you can also have things like acid fluids. So acid fluids, acid waters can probably also do bleaching. So you can think of things like cranberry juice, orange juice. Those kinds of fluids are acid, and even those, maybe if you think about it as being a little bit stronger, those kinds of things could actually do some of the bleaching and mobilize iron. People think that some of the rocks on Mars probably got bleached by acid fluids. And maybe some of those acid fluids were related to volcanic outgassing, some of the gases that come out of volcanoes. People have actually done some studies of acid mine drainages here on Earth. And some of those places where you have these very acidic waters, where they've brought certain minerals like pyrite up to the surface, and it interacts with water, it produces an acid. And those are places where there's been a lot of mobilized iron. And so people are thinking probably acid waters could be responsible. Some things that could help the acid waters if you had elevated temperatures. So if you had hydrothermal fluids, that might also be a way to get some bleaching. And people have looked at some more isolated areas on Mars and proposed that maybe there have been hot waters there in the past. Based on studies, would I say that there's been microscopic life on Mars in the past? I honestly do not know. And probably 20 years ago, I would have said, you know, I just don't even think that's realistic. I would say now I'm a little bit different. I still don't really know that we would see it. And even if we saw it, I don't know if we would recognize it. But I think the bottom line is that I am hopeful that there is microbial life on Mars, because I think that would be a real exciting find. But I honestly don't know. Yes, so the question is, even though there have been soils that have been studied on Mars, we haven't actually found any hard evidence that those soils actually involved life, and that's true. We have to wait and see. I think this is a case where we have this bias of Earth equals 1. When we look at soils, every soil on Earth has been affected by life, and life has helped create those soils. You know, plants create these different plant horizons and such, and it breaks up the rock. But, you know, on Mars, are there just physical processes that are actually contributing to this quote-unquote soil? It's really kind of a regolith, or it's broken up rock. It has different kinds of properties, and so, you know, does that mean that it doesn't have life? We don't know. Oh, that's a good question. Have we found any concretions on other planetary bodies? The moon is largely basalt, and so we have to have concretions largely where there's porous rocks, and basalts just aren't that porous. And so we haven't seen any on Mars. And the only place that we've seen them so far is on Mars, where we have this high resolution data and where we can actually have the rover on the ground taking close pictures. But I think what's remarkable is just how many places on Earth there are concretions. I think you can literally go to every continent and somewhere, you know, there are concretions. And people have told me, you know, about concretionary looking things in Antarctica and, you know, all over. You can go to New Zealand, Australia, and you see a lot of the coloration and the mobility of iron. And concretions can be multiple compositions, and they can be, you know, many little sizes that you probably, I've stepped over, you know, millions and billions of them in southern Utah, and I haven't paid much attention to them. And I really only started paying attention to them about 20-something years ago. So they are everywhere on Earth, and it's kind of remarkable. And since they do form on Mars, it's kind of plausible to think if there are mobilizing elements and there's water, why not have them on other planetary bodies? Yes, that's a good point. Is all the good stuff going to be buried on Mars, and are we going to be able to do some coring? And so the answer to that is right now we do have the capability of doing some coring, but it's very limited and it's fairly shallow. And one of the ideas is that we don't see surface water on Mars, but is there subsurface water on Mars? And if we were actually able to drill down, would we be able to detect that? So there are a variety of reasons why we think that coring would be nice. And if there was life and you have all this radiation that's going on the surface of Mars, maybe life would want to hunker down lower for protection in the crust. And so those are things that people are thinking about. Some of the next missions are actually planning to do more coring and actually planning to do some sampling and bringing, they're not bringing the rocks back yet. What they're going to do is collect the rocks in a pile. Maybe it's only about a dozen or so, the Mars 2020 mission. And then they'll put them in a pile, and then your generation has to figure out how the rocket fuel and everything else can be sent to Mars to send those samples back here to Earth. So those are things that are in the works. Oh, is it a form of crystallization? The concretions are sand grains that are cemented together with a mineral. And that mineral can be crystalline, it can be sort of more amorphous, like it depends on what the composition are. But the cement is made up of a mineral. And you know, minerals by technicality have certain characteristics and have certain mineral forms. So they are crystallizing or they're precipitating at usually Earth's surface temperatures and pressures. Does that answer your question? They're finding the blueberries on Mars, and those blueberries have a lot of the hematite. And it is a fairly crystalline hematite, and that's why it's sort of this grayish blue color, because it's a bigger grain size. When you get hematite and it's a smaller grain size, it's kind of more reddish, earthy color rather than the bluish metallic looking color. It could be, temperature could be involved. It could be other things though as well, like just what the composition, exactly what the composition of the fluids are, and maybe how long it has to actually crystallize, or even what, or to precipitate, or even exactly what the concentrations of the mineral actually are. So there's a lot of different factors that might be involved. And that's partly why we have so much variety here on Earth. Anything else?
Great. Well, let's give Mark a hand.
Thank you.